Good day, everyone. Welcome to the course on computer organization and architecture. This course is designed for undergrad students who are new to the computer organization and architecture world. So today is the first lecture of the course. And in this lecture, our aim is to familiarize you with the contents of the course, and why we need to go through this course, computer organization and architecture. What is the need of this course, and what are the objectives, course objectives that we are going to achieve, and what will be the structure of the course. So this is what we are going to address in this particular lecture, and at the end I will present the complete structure of the entire course. So let's start the lecture. The first thing that we have to understand is that, for example, you have gone through the computer programming course. You may have gone, everyone who is learning computer organization and architecture, he may have clearly done the computer programming course. And in the computer programming, you may have chosen some language, some programming language, for example, C, Java, Python, or any other language. And using that language, you are writing programs, and those programs are used to achieve some objective. Okay, so in your C programming, you were considering in your computer programming, you were considering your programming language as a model of computation. Okay, and this computer programming, we can say it is the programmer's view of a computer system. This is how programmer views the computer system. For a programmer, a computer system is a kind where we write a program and that computer system will execute our program. Okay, so we can also say this is the software view of a computer program. And likewise, you may have gone through the digital logic course. What we are doing in digital logic? In digital logic, for any computation, we view this digital logic as a model of computation. We connect the gates with each other to perform some particular function. Okay, so we can say the digital logic is the hardware designer's view of a computer system. Actually, what we want to achieve, basically the main aim, what is happening in the computer domain is the programmers write the program, and finally we have to execute that program using the digital logic. Or we can say we have a program and we have to execute this particular program using the logic gates. How can we run this computer program on a logic gate? Okay, this will be the main objective of this course. How we can use the digital logic to execute the programs in higher level language. So whatever is in between the computer program and the digital logic, this will be the main focus of this course. There are many different layers in this midway. So in this middle one, what we have to discuss is how we convert this higher level program into a set of instructions such that that set of instruction can be executed on a digital logic. And this middle portion, which lies between the software view and the hardware view, this is we call the architect's view. Okay. And how to design a computer that meets system goals, this comes under the middleware. And the choices that we made in between these layers, in between the software layer and the hardware layer, that critically affect both the software programmer and the hardware designer. If the computer programmer knows the actual architecture or actual working of these layers, which lies between the computer programming layer and the digital logic layer, he will be able to efficiently write it as computer program. And one of the layer in this middle is the system softwares layer. And the two important system softwares are the operating system and compiler. So the operating system won't be the main focus of this course, so let's leave it here. Let's see about the compiler. What is the functionality of this compiler? Basically, you may have seen in your previous courses that a compiler is a software that converts a higher level language into machine level language. So before understanding this, converting higher level into machine level, we will come back to this. Let's first see what is the meaning of this machine language. Okay, then we will briefly discuss about the functionality of a compiler. So on the top, we can say we have a high level program, and below it we have a digital logic. Basically, this digital logic, it comprises of gates which are connected to each other, and we know these gates, they understand only zeros and ones, binary. Okay. So before discussing this digital logic circuit, one thing that we have to understand is that whenever we want to design some circuit, for example, I want to design a circuit. Okay. But before designing a circuit, I have to define the objectives that I want to achieve using this circuit. Or we can say that I have to define the functionalities that my circuit should achieve. What type of functionality should this circuit achieve? For example, if I want to design a circuit for adder, so I should design the circuit in such a way that I will define what will be the input of the circuit and what should be the output. Okay. And input, what will be the input? Basically, input to a circuit is a stream of ones and zeros. Okay. So every circuit takes a stream of ones and zeros, and based on the pattern of ones and zeros in a string, it produces an output. So we have a logic circuit. It takes input, a binary stream, and it gives us some output. Okay, so we have to, before designing a logic circuit, we have to define these binary streams. What kind of binary streams should our logic circuit expect, and what should be the output? These binary streams, we call these binary streams as machine instructions. Okay, so we give machine instructions to the logic circuit, and based on the type of instruction, it gives us the output. So for every logic, we have a set of instructions. And this set of instructions, it takes as an input, and based on the type of instruction, it provides us the output. We can also say that this set of instructions will define the functionality of our logic circuit. Okay, so first of all, for designing a circuit, we have to define the functionalities that we want to achieve using our circuit. So the first thing when we are designing a circuit is to define the functionality. Or we can say define the set of instructions. So when we define this set of instructions, okay, so up to this point we are not designing anything. We are simply, it is our software approach to see what should our circuit perform, how it should work, what kind of input it should take, and what should be the expected output. So after defining these set of instructions, we design a circuit. Or we can say we design a digital logic. Or in other terms, we say we design a chip. This is we can say layman term, design a chip. So this chip, when we progress through the course, we will not use the chip word, we will use some other, for example, course or processor or pipeline. So this chip, this digital logic, this chip has a set of instructions. And this chip can only understand this set of instructions and nothing else. Okay? If we want to achieve any functionality using this chip, we have to write a code based on these instructions. Okay, for example, I want to search an element in an array. Okay. So I have to write a program, but that program should have instructions which belong to the set of instructions which this chip is understanding. Okay, then only it will be able to search an element in a string. So if I give some other instruction which is not in its set, some other instruction, if I give that input to the chip, it will not provide the desired output. So in our program, all the instructions should belong to this set of instructions based on which we have designed the chip. Okay, so for designing any chip, for designing any logic, what is the first thing? The first thing is to define functionalities. That means define the set of instructions. After defining the set of instructions, second thing is to design the actual circuit. Or in other words, we can say when I have the set of instructions ready that I want my logic to execute, I have to implement implement this in logic. Implement set of instructions in logic. That means design a circuit that should be able to execute these instructions. Okay, so this set of instructions, we call this set as instruction set architecture, ISA. The set of instructions is the ISA of a chip, instruction set architecture of a chip, or instruction set architecture of a processor. And this actual implementation, the actual implementation of the set of instructions, this actual implementation is called organization, or we can say micro architecture. So instruction set architecture is the set of instructions that we want our circuit to execute, and the actual implementation of this set of instructions in logic is called the organization or microarchitecture. Okay, so I hope up to this point you are with me. You understand the term instruction set architecture and organization or microarchitecture of a processor. So every processor, before designing a processor, processor is a digital logic circuit. Okay, so before defining a processor, we have to define the instruction set architecture, the instructions that we want our digital logic to execute. After defining the instruction set architecture, we implement that instruction set architecture using the hardware. And this hardware implementation of an ISA is called the micro architecture of that particular ISA. And this ISA in computer terminology is also called architecture. Okay, so let's go back to our first discussion. What was the discussion? We have a program and we want to execute that program on a logic, digital logic. But we know when we have a digital logic, we have designed this digital logic after defining the ISA. So we have these set of instructions, and this digital logic will be able to execute these set of instructions, ISAs. And this set of instructions, basically it is the binary instructions. These are the binary instructions, which we also called the machine instructions. Machine instructions of this particular machine. Okay, so we have a program and I want to execute this program on this digital logic. Okay, so how I will execute this? I will take a compiler. I will design a compiler for this particular ISA. Okay, what will be the functionality of this compiler? It takes this higher level program as input, and in the output it produces the instructions which are in the instruction set architecture of this digital logic. So it produced a program, new program, which contained only those instructions which this logic can execute. Okay, after giving this instruction set, or after giving this machine code as an output, we can directly implement this, we can directly execute this on the digital logic. Okay, so we can say the ISA or architecture, it acts as an interface between the hardware, between the software, or programmer, between the software and hardware. So ISA acts as an interface between the hardware and the software. Okay. So what we saw that for every digital logic or for every circuit or for every processor, we have an ISA, instruction set architecture, or we can say we have an architecture. And this processor can execute instructions which are in its ISA. Okay, and this implementation of an ISA, this processor implementation, actual implementation of an ISA, this is called the micro architecture. Okay, and in this ISA we have what we have, the set of instructions, and these instructions are binary instructions. But we know that to memorize binary instructions is very difficult. So in most of the languages, in most of the ISAs, they are not written as simply as binary instructions, but each binary instruction is given a symbolic notation. Symbolic notation which can be memorized easily. Okay, and the symbolic notation of a binary instruction or a machine instruction, that is called assembly instruction. Okay, so instead of directly representing ISA as the binary instructions, we represent them in terms of assembly instructions. For example, there may be some ISA which has, let's say, 20 instructions. So all instructions will be represented in the data sheet in terms of assembly instructions. So between every assembly instruction, between an assembly instruction and binary instruction, there is a one-to-one mapping. Every assembly instruction maps to one binary instruction. But the similar case is not with the high-level instruction. This case is not with the high-level instruction. Every high-level instruction may result in 2 or more binary instructions. So, but for assembly instructions, there is one-to-one mapping. Okay, so the compiler takes high-level program as an input and produces assembly program as an output. So assembly program contains those assembly instructions which are the representatives of binary instructions in the instruction set architecture. And this assembly program is given as input to another software called assembler, and this assembler provides machine program which can be executed by the machine program. And this machine program contains instructions, only those instructions which are in the ISA of a processor. So we can see here what we have is we have a problem, some problem, and we want to use electrons to solve our problem, because at the end, at the digital logic end, we have electrons. So using electrons, we design a circuit, and using a circuit we have digital logic. And if we have a problem, we make a program to solve that problem using some programming language. Okay, and we give this program to a software, to an operating system, and to a compiler, and this compiler, this software converts this program into instructions which are in the ISA of this digital logic. So this software converts the program into the machine specific ISA, and every machine specific ISA has a microarchitecture. Microarchitecture means actual implementation of this microarchitecture, and this microarchitecture is designed using these logic gates. So this is the complete workflow or the levels of transformation that the problem has to go in order to get executed by the electrons. And in our course, we will mainly focus on the ISA, instruction set architecture, and microarchitecture. We will also discuss some part of digital logic and some part of software layer, but only minimal. Okay, the main motive will be the ISA and the microarchitecture. So one thing you have to note down here is that the levels of transformation, the transformation here, the one layer is independent of the another layer, or we can say the lower layer hides its functionalities from the upper layer. So the upper layer does not care what is happening into the lower layer. Okay, for example, if I have an ISA 1, I can replace this ISA 1 with some other ISA 2. It should not affect the functionality of the software layer. Okay, so the upper layer is independent of the lower layer. So, or we can say when a programmer is designing a program, when a high level language programmer is designing a program, he does not really need to know what the ISA is. He should write the program independent of the ISA. And he is not required to know the actual implementation of this ISA. So he has to only care about the layer, about this layer, programming layer, and how to program its code efficiently. He is not required to go through the ISA layer or through the microarchitecture. He is not required to know about he is not required to know the details of these two layers. Okay. I hope you have gone up to this point. You are with me. Everyone is with me. So, the second thing that I want to motivate you that in some cases, for example, there are some applications, let's suppose MATLAB is there. So another application, GCC is there. So there was an experiment, there was one paper, research paper in the Unix conference. So that was showing that when we run MATLAB and GCC on multi-cores, there is slowdown in the performance. And this slowdown was different in MATLAB case and different in GCC case. Okay, so can we answer why there is a slowdown? Why there is disparity in slowdowns without knowing how the processor executes the program? So will you be able to answer this question? The second question is, if you are able to answer why there is a slowdown, can you solve the problem without knowing the computer architecture, without knowing what is happening underneath? For example, I am a programmer. Okay, I have run MATLAB program and I am running this MATLAB program on one processor and on another processor, and it is showing different performance on these two processors. So will I be able to answer the questions, for example, why there is a slowdown Okay. And if there is slowdown, if I know the answer why there is a slowdown, can I solve the problem? Okay. Without knowing the underneath. So without knowing the underlying of this program, what is happening under this program, I will not be able to not only solve the problem, I will also be not able to know the reasons for disparity in slowdowns. Okay. So computer architecture course, computer organization and architecture course, in this course you will be able to answer such questions, because you will be able to know the reasons that may have resulted in this kind of slowdown. Why you will be able to answer such questions? Because you will understand what is happening underneath the program, how the program is actually executed on the digital logic. So when you know the actual implementation of an ISA, when you know the ISA of a processor, you will know how this particular program works in a single core scenario and in the multi-core scenario. Not only this, after finding out the solution, you will be able to answer where, in which layer should I place my solution. What is the right place to solve the problem? Whether I should do it in the programming layer, in the ISA layer, in the microarchitecture layer, or in some other layer. So this is possible only after going through this course, after knowing the actual working underneath the program. Okay. So this was the brief idea about the processors, what we are going to discuss in this course. One, the main two topics is instruction set architecture, the architecture of a computer system, or we can say the interface between the hardware and software. Okay. And the second thing that we are going to discuss is the microarchitecture. How will we design a digital logic for a particular instruction set architecture? So if we have to define the computer architecture or computer organization and architecture, if I have to define this, if I have to define computer organization and architecture, or we can say the architecture, it is the art of designing, selecting and interconnecting hardware components. Designing, selecting and interconnecting hardware components, and designing hardware software interface. So designing hardware software interface is called architecture. Okay. This part is called the architecture. This designing hardware software interface, or ISA. And then designing, selecting and interconnecting hardware components. In order to implement this architecture, this is called organization or microarchitecture. One thing to note here is that for one particular ISA, there may be multiple microarchitectures. What is the meaning of this? What is this microarchitecture? Microarchitecture is basically the implementation of ISA. For example, in ISA, there is one instruction for addition. Okay. So in ISA, we have one instruction for addition. And when we are defining the microarchitecture for this ISA, one microarchitecture will implement this addition using a simple adder. or carry look ahead. And another microarchitecture may use a different implementation for adder. So we have two different microarchitectures for the same ISA, because this is using different implementation for implementing a particular instruction, and this is using the different one. So for one particular ISA, we may have multiple microarchitectures possible. Okay, so you have to note down this point. So this is one definition of computer organization and architecture. So designing, selecting and interconnecting hardware components and designing hardware software interface to create a computing system that meets functional, performance, energy consumption, cost and other specific goals. There is another definition of the computer architecture. Only architecture, not organization. Architecture is describe the attributes of a system. What are the attributes of our system? Functionalities, structural and functional behavior, and functional behavior that is seen by the programmer. So when we have a processor, we are not going to describe the complete processor, the details, for example, the processor pipeline, the memory system, the cache levels to the programmer. Instead, we only describe the architecture, or we can say we only show the instruction set architecture to the programmer. Based on that instruction set architecture, or based on the architecture, the programmer can easily understand the actual architecture or actual microarchitecture of the computer system. Okay. So the main objective of this course will be, so designing of ISA, trade-offs associated with the ISA, and major components of a processor. So this is one course objective. The second is design and implement this ISA. These are the two broad course objectives. Okay, and the complete course, if we see, we have divided into three parts. The first part, in the first part, we will go through the language of bits, and also we will learn about the assembly language, or we can say we will learn about the ISA. We will take some ISA. For example, there are different ISAs. You may have heard the name. ARM is one ISA, MIPS is the another one, x86 is another ISA. So there are numerous ISAs available in the market, and for every ISA there is a microarchitecture, associated microarchitecture. So we will take a language of bits. We will understand how binary arithmetic is done, how floating arithmetic is done, how they are stored in the computer memory. We will take some ISA and describe an assembly language and how this ISA is represented in an assembly language. So this is the first part. Okay. After this first part, we may have understood the instruction set architecture clearly. After understanding we can say this is the software approach, or this is the software part of this course, and software engineers are associated with this part. So after the first part, we may have understood about the instruction set architecture. Then our aim will be to implement this ISA, instruction set architecture. And for implementing this, the first thing that we have to do is to learn about the building blocks. Building blocks, for example, gates, registers, memories, how they are actually implemented. Okay. After learning about the building blocks, we will discuss how we can use these building blocks to make small circuit for performing computer arithmetic. Okay. Then from here, after the building blocks, designing of building blocks, after defining small circuits that will be used to perform different functionalities, we will discuss the actual processor design of this ISA, this particular ISA, which we may have learned in the part 1. Then after designing the processor, the fourth one will be the pipelining. So pipelining is basically improving the performance of a simple processor. So I will discuss it there when we reach it here. So let's leave it here. So up to this point, we will be knowing about the processors, simple processors. Then our objective will be to supplement these processors with a memory system to improve the performance of our simple processor. And if time permits, we will learn about the multiprocessors. And finally, the input output. So this will be the main structure of the course. The first thing that we are going to discuss is the ISA, the simple ISA. What is an ISA? What are the what makes the ISA? What differentiates it from the microarchitecture? Then we will go through the language of bits. Then we will take some ISA and learn about that particular ISA. After that, we will design some basic building blocks and the computer arithmetic using the circuits. Then we will design the processor for this particular ISA, and we will have a separate lectures. We will have separate lectures for the pipelining. And then after we design the processor with some stuff to improve its performance, then we discuss the memory systems and memory hierarchy that is present in our processors, and we will discuss the multiprocessors and input output. So this will be the complete structure of our course. So, and this is also the end of lecture 1. We will meet in the next lecture. Till then, goodbye.